Picking up from part one, we've identified sites that we wanted to visit, Upsall Hogback and Soda Lake in the Carson Sink of western Nevada. Both of these are phreatomagmatic volcanoes, meaning that they interacted with water, Soda Lake being a maar and Upsall Hogback being a series of tuff rings. So after visiting the sites, it was apparent that Soda Lake didn't have well indurated tuff, and that tuff had not been altered. There wasn't much palagonite development, in fact none at all through most of the maar volcano. So Upsall Hogback became the focus of the study because it did have indurated tuff, it did have palagonite development, and upon returning to the lab we found that we did have some PBA. So I went back to Upsall Hogback again and did some mapping. And what we get is a complex of tuff rings, the northern ring being the largest. I named these just by geographic location within the complex, so Upsall Hogback North, Central, which is actually composed of at least 2 rings, and South, which may have been multiple rings, but has the appearance of more or less just one now. And the confluence of the southern and central rings is one of the most interesting places in the complex. For scale, Upsall Hogback North is about a kilometer, a little over a kilometer in diameter, kilometer and a half. But the best tuff was at the confluence of the central and southern rings. And with some mapping, you can see these teal areas pop out at some of the higher points in the complex in certain points. So what are those teal areas? Those are calcareous mounds called tufas. So these are something that are particular to places where groundwater that upwells that has a high concentration of calcium carbonate in it reaches the surface, whether usually subaqueously. We found those at Upsall Hogback and they were really large and unique. I'll show you those. And the best tuff was coincident with these calcareous mounds. So again, we were looking for a wet eruption environment, and we found that evidence of that at Upsall Hogback. These forms are called bomb sags, and they occur when a bomb, remember that's a 64 mil or larger basaltic clast or accidental, is ejected from the volcano. And when that bomb lands, if the tuff, the previously deposited layers of tuff, are wet or saturated, then the bedding will bend instead of breaking. And we see that here. This is a nice bomb sag. There's another bomb sag. We also have some scouring, which is evidence of some high velocity pulses of eruption, where we get ash scouring the surface and then depositing some complex shapes. So we did have a wet eruption. There was also some lapilli encrusted with fines, which could be evidence of a wet environment, or perhaps just a wet environment and that it was raining that day. But the bomb sags are a little bit more strong evidence of saturated conditions. So we had the right kind of conditions. Notably, the tuff itself did have vacancies, which means that there was probably water in it that has since evaporated or left. So back to these tufas. Now this picture, just to leave Upsall Hogback for one moment, this picture is from Soda Lake. These are tufas at Soda Lake, and they're really interesting forms. Again, this is calcium carbonate, and this is forming from the emanation of groundwater and the precipitation at that point of calcium carbonate. Micrite, usually very fine. And Soda Lake has these for some extraneous reasons that aren't related to volcanism necessarily, but Upsall Hogback has them too, and they do occur, tufas, around the Great Basin, particularly at places with hot springs. So at Upsall Hogback, returning to our field site, we have tufas, but they're very different in form. So this wall behind me in the picture is a wall of tufaceous material. So it's all calcium carbonate, and the walls are about 20 centimeters typically, up to 60 centimeters thick, and they form rings. Rings on the ground, and within those rings there's well-preserved tuff. Chicken and egg problem, whether the tuff is preserved because of the tufas or the tufas are there following the tuff. The tufas had to have come after the tuff, but it's the calcium carbonate emplacement that has preserved both. Of course, the tufas wouldn't exist without it. So they're really unique features to come across in the field. This is a wide open desert. Upsall Hogback sits above the desert floor, up to about 60 meters above the desert floor. and it's got these mounds on top of it, a couple of which are about the size of a school bus or larger. And they're very interesting, and again, notably the best tuff, the most indurated tuff with palagonite development occurs where these tufas are, likely because of there being a foci of hydrothermal system, warm water. Calcium carbonate likes to precipitate in warm water, just like it would in your tea kettle or your water kettle. So the tufas at first were passively interesting, notably that they were coincident with the good tuff. When I took a survey of tufas on the site using GPS coordinates, we found that the elevations when plotted were interesting. And they, when plotted it with the lake history of Lake Lahontan in this upper part of this diagram, they told an interesting story, one that seems apparent. So the larger cluster is approximately at the right elevation to have occurred when they were near the water surface for a given length of time. So is a smaller cluster, a little bit of variance there. That can be expected. Of course, this is a site that has been around for several thousand years, and there has been some isostatic rebound, so we'd have to unravel that whole story, which isn't the focus of this thesis. But nonetheless, we can say that Upsall hogback had to have existed as tuff rings before these tufas were emplaced. So we know that Upsall hogback had to have been emplaced prior to 19,000 years ago, which is a new thing. Previously, there was only a lower age limit, so we knew that it was emplaced after 33,000 years ago based on some carbon dating of samples from stratigraphic layers below Upsall hogback. But now, correlated to the GISP2 ice core, we know that it had to have been placed prior to 18,000, 19,000 years ago. What did we find petrographically? Petrographically, olivine occurs often with poikilotic opaques, which prove out to be magnesiochromite, as proven by micro X-ray diffraction and Raman analysis. The tuff is 42% glass by volume. We've got almost a third of it is primary pore space, vesicles and whatnot, and we've got 7% only of olivine and plagioclase, which is actually not that low for the type of material we're dealing with, but in the grander scheme of things, it's crystal poor. So mostly we're talking about glass, which is great, and lots of pore space, which means there's lots of room for warm water to percolate through the system, which is really good for finding PBA. Now, interestingly, this thesis doesn't focus on the petrography. That's a whole other story, but I did work on that, and what I found was that fractional crystallization probably occurred from north to south at the complex. So that means that the northern ring probably erupted first and then the southern rings, and I can demonstrate that with plagioclase and olivine fractionation using Pierce element ratios. So we're seeing a decrease in magnesium and calcium. So probably we have a good direction of magma flow. This is all a monogenetic system. So we know that the system was one magma body that erupted in a few instances, probably over a geologically brief period of time. So what is the main finding in the tuff that relates to PBA? Well, we did find PBA. They're poorly developed, though, compared to other studies. These typically are 5 micrometers or less, which is very small, but being poorly developed is not necessarily a bad thing. This shows us an early developmental stage, which might give us a better clue as to the mode of colonization of the rock by these microbes. And what we found was that most of them are in vesicles. Cracks are less seldom developed here. So they seem to find a happy place in vesicles. And we find that because of the limitations of the development of the PBA at Upsall hogback, the typical classifications used for marine basalts where this occurs aren't a good fit because we have limited morphology and size. So I adapted to that, simply classifying them as granular PBA, which is what we see in the lower left, microtunnels that are less than 5 micrometers in length, so that's the really not very well developed, and 5 micrometers and longer, which is more like this guy in the middle, which are fairly well developed. The microtunnels almost all emanate from vesicles. There are certainly instances from cracks, but at cracks we more generally see granular development. There are differences between microtunnel types between vesicles. Sometimes we see them choked off in calcite-filled vesicles where they haven't developed quite as well. And that becomes part of the story. Remember that this is in the most well-indurated tuff is where we find these textures, and the most well-indurated tuff is in association with our tufas. So these foci of hydrothermal systems where we have calcium carbonate precipitating. So what do they look like? Well, we have our terminal enlargements, which we had hoped to see. We have annulations along the microtunnels, which is good, and we have bifurcation. So this is all good for biogenicity. They're complex shapes. The morphology varies, and sometimes we do see directionality. Not often, but often they're not avoiding things, but they bend in the same way and not simply perpendicular to the vesicle wall. At times, as you can see here, we do have microtunnels. The more fine type is the typical type if we're going to find them at cracks that we would find. We find the better ones, the more well-developed ones at the vesicles. So remember I said size distribution is part of the story of biogenicity. And what we look for in size distribution is that we want a log normal distribution of those sizes. And log normal indicates biogenicity because of reasons relating to multiplication versus addition. And what we found at Upsall Hogback is that even with the poor development, which is to say early development, I shouldn't say poor, the microtunnels still have a log normal distribution, and the sizes are still sufficient such that microbes would inhabit them. We have diameters of 3 micrometers or less typically. So we're still looking at something that would be a good habitable environment for, or a result of, microbes. Syngenicity we can prove out using the stratigraphic relationship of most often calcium carbonate, which entombs microtunnels. In this instance is a very nice example where we have open vesicles. We saw this earlier, open vesicles with good microtunnel development, large terminal enlargements, a couple more down here, empty vesicles, and then we have calcite-filled vesicles. And interestingly, the calcite-filled vesicles have poor microtunnel development. So what we might infer from this is that the calcium carbonate has truncated the growth of the microtunnels by choking them off. Remember that the microbes that are emplacing or creating these ichnofossils need to respire somehow just like we do. So when we breathe out carbon dioxide, hopefully we have enough airflow that the carbon dioxide doesn't fill the room and choke us off. Similarly, the microbes are going to be respiring, they're going to be metabolizing, and waste products need to be taken away. So if they get choked off by calcium carbonate, then there's no more respiration possible. There's no more removal of those products. So we know that these probably formed during the hydrothermal system while it was altering the glass. That's also borne out by the occurrence of palagonite, which overprints the microtunnels, which means that the glass was being altered. Remember, palagonite is the hydration of this glass, or the result of hydration of the glass, and that overprints the microtunnels, meaning that the microtunnels had to have, at least some of them have been there before the palagonite. So our secondary minerals, we talked about carbonates, and using some analogs from around the basin of active hot springs that still exist, I've estimated that paleothermometry estimates indicate 15 to 55 degrees Celsius for the temperature of formation. That's based off of carbon and oxygen stable isotope analysis and using Copeland 2007 as our model. We do have pure calcium carbonate via X-ray diffraction. We also have palagonite observed petrographically and smectites, which came up through our X-ray diffraction, bulk and micro. And so we have also zeolites, which we haven't seen in pictures yet, but they were identified by X-ray diffraction as well, primarily by bulk. And the zeolites are an interesting part of the story regarding temperature. We also have nontronite. Now, nontronite forms on olivine grains when a temperature is sustained at 120 degrees plus. We don't have that in Upsall Hogback samples, so we know that the temperature that high wasn't sustained, which is good because that really narrows down the number or quantity or likelihood of microbes persisting in the system. So let's try and constrain the environment. What we know is that about 30% of the glass that I've observed in a thin section of Upsall hogback tuff is palagnetized with PBA. And so we're looking at samples with PBA then, because that's what's relevant to our environmental constraints. Now there's a lot more gel palagonite than fibropalagonite, and fibropalagonite forms at slightly higher temperatures and a longer duration, which is good for us if we want to keep a warm, happy, but not too hot environment for microbes. Now, given that we had 30% that's been palagnetized, previous studies found that at about 60 degrees Celsius, we get less than 40% of glass. So we know that we were probably below 60 degrees Celsius, and at 40 degrees Celsius, you're going to get less than 5%, and we have more than that, so we have a temperature bracket of at least 40 to 60 degrees Celsius sustained based on palagnetization. Doing some math based on typical rates of palagnetization, we could estimate at that temperature we probably had about 20 to 80 years of hydrothermal systems. You can imagine this volcano erupting and wet groundwater, wet substrate with lots of groundwater enriched in calcium carbonate being heated and percolating, and then slowly that system's cooling down as the remaining magma cools in situ or recedes. Now the zeolites tell a bit of a different story. We have three main zeolites that occurred based on X-ray diffraction: phillipsite, chabazite, and analcime. And from what we can tell from these is that the temperature was at least 55 degrees Celsius, although probably warmer because vapor phase isn't necessarily what we're looking at, although it could be within the vesicles. Even though we're in a saturated tuff, within the vesicles it may not have been saturated, so vapor phase is possible on those, and of course we don't know that for sure. So then what have we got for the environmental constraints? We know 40 to 60 degrees Celsius based on palagonite, probably at least 68 degrees based on our chabazite zeolite, and under 120 degrees Celsius because our olivines are not altered on the rims. Based on calcium carbonate precipitation in the form of calcite, we have alkaline water. And we have a lot of water-rock interaction that's based on the penetration of calcite deep into the rock in the vesicles. We have high porosity in our rock. They're great conditions for the microbes to live. So the tufas, as I said, occur most frequently with the most well-indurated tuff, or vice versa. The most well-indurated tuff occurs in coincidence with the tufas, and that was consistent. Is this causal or is this preservation? So were there nice examples of well-developed or reasonably well-developed PBA that occurred in places without tufas and they weren't preserved because there weren't tufas? I would suggest that it's not an accident that this is not just preservation. I think that the likelihood of these existing only in pockets where there's a nice upwelling hydrothermal system is strong, so probably this is correlation, and probably causation is related to the hydrothermal system. Of course, it's not surprising, but here we see it in practice and we see it in the results. So what have we got? We have our temperature constraints, probably 40 to 60 degrees Celsius. That's not strictly speaking up and down, or steady. It is up and down. This is a natural system. This is all based on a hydrothermal system. We have PBA in this basaltic glass in a lacustrine environment again, which is wonderful. And the PBA is in association with calcium carbonate, palagonite, and a zeolite assemblage. We have nailed down a bit of a time constraint for Upsall hogback, and we know that Upsall hogback is monogenetic, probably have an eruption order as well. So what can we do with this information, particularly regarding the environment that the PBA form in? Well, the Mars 2020 rover, Perseverance, is going to Jezero Crater, and Upsall hogback is probably a good analog, Earth-based analog for Jezero Crater. They both have olivine, they both have smectites, probably hydrothermally derived. They have carbonates, probably hydrothermally derived. They have desiccating lakes. So there's a lot of similarities here. And I think that Upsall hogback could provide an instructive example of the type of rocks that we want to look at in Jezero crater, potentially for sample return. And that could be some of the first direct observations of fossils, so not direct observations of actual life doing its thing, but we're looking for evidence of life, and this could provide the ichnofossils which demonstrate to us that life did once exist on Mars in the most likely form, which is microbial.